Hi everyone, I'm Ifan. I'm glad to introduce our work, Noto Point Echo, which is a highly efficient point-based detector for 3D LiDAR point clouds. Given a LiDAR point cloud, the task of 3D object detection is to predict the category as well as location, size, and orientation of the object. The main limitations of existing methods are: first, the majority of approaches are focused on voxel-based framework, while point-based 3D detectors are still underdeveloped. On the other hand, methods such as point-GNN and 3D SSD can directly process point clouds, but all of them rely on time-consuming processing or expensive memory footprints. Furthermore, they are limited to small-scale point clouds and can only achieve the single-class detection mode. Therefore, the question is, can we develop a LiDAR detector that can process point clouds directly and achieve multi-class object detection in a single pass? Second, the network should be computationally and memory efficient to process large-scale point clouds. Finally, the network should be also accurate and scalable to more complex scenarios. For point-based processing, the foreground points are more important for object detection, so we aim to build a task-oriented, instance-aware downsampling framework. The key problems of the downsampling are: first, effective point sampling to preserve foreground points, especially for small and sparse instances. Second, the sampling method should be efficient enough. Motivated by this, we first started to qualitatively evaluate different sampling approaches. In detail, we follow the commonly used four-layer encoding architecture and report the instance recall at each layer. We find it remains challenging to precisely detect the small objects such as pedestrians and cyclists with only extremely limited foreground points. To preserve more foreground points effectively, we propose two task-oriented sampling approaches by incorporating the semantic priors into the network training pipelines. First, we add extra MLP layers to estimate the semantic category of each point in a supervised manner. Then, the points with the top key scores are preserved for the next layer. Considering that the foreground points closing to the centroid are helpful for final object detection, we further propose a centroid-aware sampling method to give higher weights to points closer to the instance centroid. We evaluate the performance of the proposed instance-aware downsampling and find it can achieve high instance recall with also accurate detection. Additionally, it is extremely efficient. Then we show the qualitative results with FPS and feature FPS. To achieve accurate location for small-size objects, we leverage the contextual cues around the bounding box for instance centroid perception and introduce an auxiliary regularization term to minimize the uncertainty of the centroid prediction. Here is the architecture of IASSD. We follow the bottom-up manner to build an efficient point-based LiDAR object detector. For the experiment part, we first illustrate the performance and efficiency of our IASSD. It can achieve highly efficient and accurate performance on the KT benchmark. Then we evaluate the performance on the KT test benchmark. We can see that IASSD achieves superior performance among all point-based methods, with even competitive comparison by powerful hybrid methods. For efficiency, as shown in Table 6, IASSD is highly efficient that can be up to inference 100 frames in parallel in a single pass, with a speed of 83 FPS on a single GPU. Here we show some qualitative results achieved by our IASSD on KT dataset. Golden points refer to the representative points after sampling, and reds are centroids predicted. We further evaluate the performance of IASSD on Waymo dataset. It achieves better detection performance on pedestrian and cyclists compared with other strong baselines. Then we show the qualitative results on Waymo dataset. To further verify the scalability in more complex and realistic situations, we also evaluate the performance on the latest WANS dataset and get the competitive performance among all baselines. We also show the results on WANS dataset. You can follow us on the GitHub page if you are interested. Many thanks.